Okay, so we're going to find the total length of all of the edges and also all of the diagonals in a regular n-sided polygon drawn inside a unit circle like this. So here in our picture we've got n is 6, so we've got a regular hexagon, all the sides are the same length, drawn inside a unit circle. But we're going to do this in the more general case, and we'll start just by finding for an n-sided regular polygon drawn inside the unit circle, what is the length of one of the edges, then later we'll move on to the diagonals. So we can just draw a smaller chunk of the picture here. We can draw a triangle where we've got one of the edges, and on the left we'll say this is the centre of our unit circle. So we're interested in the length of one of our edges. Let's call this L. And we can work out what this angle is in the centre here because we've just got n sides repeating round, so a total of 360 degrees divided by n will be this angle, or in radians it'll be 2 pi radians divided by n. So this angle here you can see is 2 pi over n, and then we can also see that each of these sides here are just going to be the radius of the circle. So because it's the unit circle, we've just got 1 and 1. And also this is an isosceles triangle, so now we can actually work out what each of these two angles are. So we know that the three angles need to sum to 180 degrees or pi radians, so the sum we need to do pi minus 2 pi over n, but then to actually find one of these angles on its own we just need to divide this by 2. So when we multiply this by half we get pi over 2 minus pi over n for either of our angles here in our isosceles triangle. And now we can use the sine rule to actually work out the length L. So we know that L over sine 2 pi over n is going to be equal to 1 over sine pi over 2 minus pi over n, like this. So then we multiply on both sides, we get L is equal to now sine 2 pi over n, all divided by sine pi over 2 minus pi over n. But actually here we can simplify this somewhat, so we can use some trig identities here. For example, on the numerator we've got sine 2 pi over n. We can actually use our double angle formula, so sine 2 theta is always equivalent to 2 sine theta cos theta, and even in our numerator we've got sine pi over 2 minus something, and if you have sine pi over 2 minus any angle theta, this is always going to be equivalent to just cos theta. So we can use both of these identities now to get a slightly nicer expression for L. So using our double angle formula we'd have theta is our pi over n in the numerator, so we get 2 sine pi over n cos pi over n in the numerator, and in the denominator this is just equivalent to cos pi over n. And you can see our two cos pi over n terms will cancel. So this gives us then that our length of one of the sides in this regular polygon with n sides inscribed in our unit circle is just 2 times sine pi over n. And now we'll calculate the length of some of our diagonals. So if you look at this picture here, let's imagine this is the centre of our circle and we've got 3 of our edges, and we're interested in this diagonal which we'll say is 3 edges apart. But we'll do this in the more general case where we go k edges apart, at least starting with the case where you see how this triangle we have a non-reflex angle, but if our diagonals were taking us all the way over on the other side of this picture where we have a reflex angle, that's a slightly different scenario we'll deal with separately. So in this case where we've got diagonals that are k edges apart, let's just copy out this triangle again, and we're interested in the length of the diagonal which we'll call L again. We know that we've got the radius here and here, and we can also work out this size of this angle here because we've got it's 2 pi over n is just the size of the angle in one of these small triangles, but we've got k lots of this, so it's k lots of 2 pi over n, so this angle is 2k pi over n radians. And this allows us now to work out these two remaining angles because we've got an isosceles triangle. The angles sum to pi radians or 180 degrees, so we do pi minus 2k pi over n, then we need to halve this to get one of the angles on its own, which gives us pi over 2 minus k pi over n for one of our individual angles here. Then this allows us to use the sine rule just like before, so we can set this up so that L over sine 2k pi over n is equal to 1 over sine of our other angle, which is the pi over 2 minus k pi over n. So then when we multiply on both sides by the sine 2k pi over n, we get L is equal to sine 2k pi over n divided by this sine pi over 2 minus k pi over n. But once again, we can simplify this using our rule that sine pi over 2 minus theta is equivalent to cos theta. So we can turn this denominator now into cos k pi over n. And actually the numerator, we can use our double angle formula again to get 2 sine k pi over n times cos k pi over n. And all of this is still divided by this denominator of cos k pi over n. So you see our cos k pi over n terms cancel, and we get then L is just equal to 2 times sine k pi over n, at least in this case where we have a non-reflex angle. And it's really interesting as well, if you have k as 1, you can see that this is consistent with our formula for an edge. So we've actually managed to generalise this now to cover lots of the diagonals, as long as we don't get a reflex angle. Now we've got two special cases to consider separately now. So before we get onto reflex angles, there is also the possibility that we could have a 180-degree angle or a pi radian angle. And that would essentially correspond to the case where our whole triangle is just the diameter of this circle. So in this case, where we've got the diameter, this is where k would have to be equal to n over 2. And you see this isn't even possible when we have an odd number for our n, but here for our hexagon where we've got an even number of edges, you can go through the diameter, which goes through the centre of the circle here. So in this case, you know that the length of the diameter, if it's the unit circle, is just going to be 2. But it's interesting to notice if we actually substitute this in and we think of this as being n over 2, k is n over 2 steps apart, we can still use our previous formula, and you can check 2 sine, so where k is n over 2, so it's n over 2 pi all divided by n. Your two n's cancel and you're just left with pi over 2. So this is 2 sine pi over 2, and sine pi over 2 is just 1, so this is indeed equal to 2. So our formula is actually consistent even for this strange case where we've got the diameter as our whole triangle. So now let's consider the case where we've got k greater than n over 2, where we get a reflex angle. So in this case where we've got a reflex angle, we can actually use our previous work where we know actually what's going to happen. If we draw this out, we've got, let's say we're k steps apart here for our reflex angle, we know that there'll be n minus k steps on the other side of this reflex angle. So we could just substitute into our formula for the non-reflex angle that we've already worked out. So we know that the length of the diagonal in this case, where it's k steps apart, is essentially going to be the same as the diagonal where it's n minus k steps apart. So never mind the fact that we're counting everything twice, we'll deal with that later, but we can say then that the length of this diagonal in the reflex case is going to be 2 times sine n minus k pi all divided by n. But then we can expand this so we get 2 sine, it'll be pi minus k pi over n. Then we can actually use another trig identity here, which is that sine of pi minus theta is actually always equal to just sine of theta. So then all of this length is then just going to be equal to 2 sine k pi over n once again. So we can actually substitute in values of k which are larger than n over 2, even though this corresponds to a reflex angle, our formula does still work. So this actually works for any value of k from 1 up to n minus 1. So this covers all of our diagonals and all of our edges, never mind the fact that we're doubling up on counting everything twice. So we'll deal with this now when we try to add together all of these different lengths. And now when we add together all of our total lengths of the edges and diagonals, it turns out it's actually going to be more convenient to calculate double the total length where we multiply by 2. This avoids having to split into cases where n is odd and n is even. So we're saying here 2 times our total length now. For example, if we start with just our edges, we've got n edges, so we'll have 2n times sine pi over n, remembering that an edge is just effectively a diagonal that's one step apart. Then if we want to count all of our diagonals that are 2 apart, there'll be n lots of these as well, so 2n times sine 2 pi over n, and we keep going like this all the way until we get to being n minus 1 steps apart. So again, there are going to be n diagonals which are n minus 1 steps apart, and these actually correspond to the edges. So being 1 step apart is the equivalent of being n minus 1 steps apart. So we end up double counting everything here. So we have n lots of 2 times sine n minus 1 pi over n, like this. So this counts all of our edges twice, and in the middle we've counted all of our diagonals twice. But the only interesting special case we need to think about now is, what about if n is even and we have all of these diagonals? Well, if we continue with this pattern, we're saying that there are n lots of the diagonals. You'll spot here that there's actually only n over 2 diagonals. So here we've got n is 6, but there's only 3 diagonals because you're counting the diagonal from this vertex to here twice as going from this vertex to here again. So we do indeed end up counting everything twice if we just use this formula like so, the sum of 2n times sine pi k over n, like this. So 2 times our total length is given by this expression, so then this tells us that our total length, we can just divide by 2, is going to be n times sine pi over n. So we've now halved this contribution, and we'll halve this contribution at the very end, so that we get our total length for all of the edges. Then all of our diagonals 2 apart get counted now. We divide by 2, so n times sine 2 pi over n, like this. Then we just keep going, and we keep going until we add n lots of sine n minus 1 pi over n. So this is a nice expression for our total length, but we can actually do some more work using complex numbers now to get this into an even simpler form. So we'll see in a second why it makes sense to use complex numbers here. We're essentially using Euler's formula that e to the I theta is equivalent to cos theta plus I times sine theta. So then if we have sine theta, this is going to be the imaginary part of e to the I theta. So sine theta is the imaginary part of e to the I theta. So we can think of all of these sine pi over n, sine 2 pi over n, and so on as imaginary parts of e to the I pi over n, e to the 2 pi over n, and so on, which will actually give us a geometric sequence. So we'll say that our total, we'll just call it sigma, the total sum here is going to be n times, if we take out a factor of n from each term, first of all we have the imaginary part of e to the I times pi over n, then the next one is the imaginary part of e to the I times 2 pi over n, and so on all the way up until we get to the imaginary part of e to the I times n minus 1 pi over n, like this, where all of these terms are still being multiplied by n. Now if you have the imaginary part of lots of different complex numbers all added together, this is the same procedure as adding up the imaginary parts separately. So you could check this with a plus bi, add this to c plus di, and the same works with any finite sum like this. So we can actually write all of this now as n times the imaginary part, where we add all of the complex numbers together before taking the imaginary parts. You've got e to the I pi over n plus e to the I times 2 pi over n, all the way up to e to the I times n minus 1 pi over n. And you can see at this point we're starting to get a geometric sequence here, so we can write this now as n times the imaginary part of e to the I pi over n, then this is just e to the I pi over n all squared. The next one would be e to the I pi over n cubed, and so on, all the way up to e to the I pi over n, where this is now raised to a power of n minus 1. So we take the imaginary part of this geometric sequence and multiply by n. So now we've got a partial sum of a geometric sequence. We'll say the common ratio here, e to the I pi over n, is r. So we've effectively got r plus r squared all the way up to r to the n minus 1. And you can show using the formula for the partial sum of a geometric sequence that this can be simplified and written as r times 1 minus r to the n minus 1, all divided by 1 minus r. So this gives us a really nice simple expression now for our total sum. We'll have n times the imaginary part of, where we can rewrite all of this now as e to the I pi over n into 1 minus, it's e to the I pi over n raised to the power of n minus 1, so I'll write it as I times n minus 1 pi over n like this, then all of this is going to be divided by 1 minus e to the I pi over n, this e to the I pi over n term being our r there in the formula. And then here we can actually expand this bracket in the numerator as well, so we'll get n times, now we'll have the imaginary part of e to the I pi over n first of all, but then when we multiply e to the I pi over n by e to the I pi over n to the power of n minus 1, we get n lots of e to the I pi over n. So this actually just gives us minus e to the I pi, where there's no n there, because we've got one lot plus another n minus 1 lots, all divided by n, so n over n just gives us 1, where this all gets divided by 1 minus e to the I pi over n, just like before. But we know e to the I pi, without any n there, this is just equivalent to minus 1, so we can actually simplify this now to n times the imaginary part of e to the I pi over n minus negative 1, so plus 1 over 1 minus e to the I pi over n like this, where we take the imaginary part of this and then multiply by n to get the total length of all of our edges and diagonals. Now before we can take the imaginary part of this fraction, let's get rid of the fact that we've got a complex number in the denominator. So we do this by multiplying on the numerator and the denominator by the complex conjugate of the denominator. So if we write our denominator in expanded form, again just using Euler's formula, this becomes 1 minus cos pi over n plus I times sine pi over n like this. And now we want to take the complex conjugate of this, so just take the negative of our imaginary part. So this turns into 1 minus cos pi over n minus I times sine pi over n, just like this. But we can keep this in exponential form here by taking advantage of some more trig identity. So here, if we've got negative sine pi over n, we can take advantage of the fact that negative sine theta is always the same as sine negative theta. So we could change this into plus I times sine of negative pi over n. And if we're changing this to a negative pi over n, we could actually do the same with our cos pi over n, taking advantage of the fact that cos theta is always equal to cos negative theta. So then we can rewrite our new denominator, our conjugate of the denominator, as 1 minus cos negative pi over n, now with a plus I times sine negative pi over n. So now we can apply Euler's formula again to see that this is now 1 minus e to the negative pi over n times I. So this is our complex conjugate. So now we'll multiply the numerator and denominator of this fraction by this conjugate, so that then we can get rid of the complex number in the denominator. So then we're going to have n times the imaginary part now of e to the I pi over n plus 1 is going to get multiplied by this conjugate, this 1 minus e to the minus pi over ni, and then in the denominator we'll have 1 minus e to the I pi over n gets multiplied by 1 minus e to the negative pi over n times I. So then if we expand the bracket in the numerator first of all, we'll get n times the imaginary part of, we get an e to the I theta, e to the I pi over n, we get a plus 1, we have a e to the I pi over n times e to the negative pi over n I, just gives us 1, but this is negative, so we get a negative 1 here, and finally we have take away e to the minus pi over n times I. So our two 1's cancel here, giving us a slightly nicer numerator to deal with. And then if we expand the brackets in the denominator now, we'll get first of all 1 minus e to the I pi over n, then we'll have another minus e to the negative pi over n times I. Then finally when we multiply these two together we get two negatives, e to the I pi over n times e to the negative I pi over n just gives us a 1, so we get a plus 1 here. So here the 1's don't cancel, but we can at least combine those into a 2 now. So we get n times the imaginary part of e to the I pi over n minus e to the negative I pi over n, Then in the denominator we get 2 minus, then we'll put this in brackets, e to the I pi over n plus e to the negative I pi over n. Now if you're familiar with the exponential forms for sine theta and cos theta, which we've just got here, you'll see that this sort of structure is starting to appear in our fraction expression. So now if we just divide on the numerator and the denominator, divide everything through by 2, we have n times the imaginary part of, first of all, our new numerator having divided everything by 2, we get e to the I pi over n minus e to the negative I pi over n, all divided by 2. So this is our new numerator having divided through by 2. But to make this look like sine pi over n, we can just introduce an I here and take an I here as well. So it's I divided by I. And we haven't changed the value of anything there. So we only need to do this in the numerator with the I, because now in the denominator, having divided everything through by 2, we get 1 minus e to the I pi over n plus e to the negative I pi over n, where this is all divided by 2, and this actually looks like cos pi over n because there's no I in the denominator there. So we can now simplify all of this to just become n times the imaginary part of I times sine pi over n, all divided by 1 minus cos of pi over n. So the imaginary part of this complex number, we've just got I times something real divided by something real. So the imaginary part of all of this is actually just going to be sine pi over n divided by 1 minus cos pi over n. So we get then our final expression for the sum of all of these lengths of the diagonals and edges in our polygon is n times sine of pi over n, all divided by 1 minus cos of pi over n. So this is our answer then to the original problem, finding the sum of all of the lengths of the diagonals and edges in an n-sided regular polygon inscribed in the unit circle.